Hey everyone, I'm your host Amir Jafari, and this is another lecture in the series of lectures on quantum field theory. Last time we talked about the second quantization procedure of the Klein-Gordon field, and we did the second quantization in a kind of rough way. We didn't pay enough attention to some technical details. For example, we didn't distinguish Lagrangian and Lagrangian density, Hamiltonian and Hamiltonian density. What's the difference here? And why did we do this? Well, I'm going to talk about the difference. Today, we're going to repeat whatever we did last time in a more careful way, adding more details and refining the previous picture. But why we are doing this? Because as I've probably mentioned earlier, my strategy in teaching quantum field theory and also other subjects, for example, general relativity and string theory, especially string theory and quantum field theory, is to give you a big picture initially, which is by definition a rough picture, right? Because in a big picture you don't have time and patience, to get into details. So I present a big picture. For example, for quantum field theory, we said that Klein-Gordon equation is a kind of, relativistic generalization of the Schrödinger's equation, but you shouldn't interpret the solution of the Klein-Gordon equation as a wave function, because functions are for fixed number of particles, and because here we are combining special relativity with quantum mechanics, the number of particles cannot be fixed. So instead, you should treat the Klein-Gordon equation as a field equation, and then find the Lagrangian and Hamiltonian corresponding to this field in such a way that, for example, the Euler-Lagrange equation becomes the Klein-Gordon equation, and then quantize the field, which means that promote the field and its conjugate momentum coming from that Lagrangian and Hamiltonian to fields, quantum fields. This is the procedure of second quantization. This is what we discussed earlier. But if you are going to do this in its full technical, way, I mean, mentioning all, details and everything that you need, then it's going to be kind of laborious, and for many people it would become kind of difficult. And I guess this is the reason that quantum field theory is difficult, because in almost all textbooks and lectures, people start with main idea, but doing calculations and doing, for example, second quantization, they do it in its full, flavor. They say everything that you need in a standard way. I think this is not going to work in a course like this, because there are so many details floating around, and if you mention all of these details, it's going to bore the audience, and it's gonna feel kind of difficult. So my strategy is to present a big picture, which is rough, and then add more details by repetition and refine the previous, picture. And as we go ahead, after a couple of repetitions, we're gonna go get into the standard picture, okay, presented in any textbook, for example. So previously we talked about this Lagrangian and Hamiltonian functions for the Klein-Gordon field, and today we are going to refine this picture and talk about some details. And we're going to talk about this same discussion in the next lecture as well, before we go to second quantization of the radiation field, electromagnetic case. Before starting this lecture, I have to also mention something about the calculation, one calculation that I promised you to do in this lecture about the connection of what we are doing here in the second quantization of the Klein-Gordon field with the Schrödinger's equation. Low energy, we should recover the Schrödinger's equation. So to show how this formalism, second quantization of the Klein-Gordon field, connects with the Schrödinger's equation, there is this simple calculation, and I encouraged you to do it yourself. But there were other questions in the Zoom meeting, and in this lecture we're going to see a couple of other calculations which are kind of similar, very simple calculations compared with whatever we will see in the future. But because this is our kind of first encounter with calculations in quantum field theory, so I'll do these calculations in some details myself. But because there are a couple of other questions, as I mentioned earlier, and these lectures are recorded, so other people might have similar questions. So we decided to have another separate session for these calculations, and maybe another one for questions and answers. So in this lecture, I'm not gonna go into the details of these calculations and the previous one, but we'll do them in a separate session. Okay, so let's start with the second quantization of this Klein-Gordon field in more technical details, in a more refined picture compared with whatever we had in the previous lecture. All right, so we have this Klein-Gordon equation. Let's start by writing this equation one more time. This is our Klein-Gordon equation in natural units. Speed of light, reduced Planck's constant are unity. And we said that you shouldn't actually interpret the solution of this equation as a wave function. It's similar to this equation in electromagnetism. This is a field equation for the vector potential. I should get rid of this probably so you can see. If you write down Maxwell's equations in vacuum, no currents, no charges, you're going to get this equation for the vector potential. No one interprets this vector potential as a wave function. So similarly here, in the Klein-Gordon case, you shouldn't interpret phi as a wave function. If you do it, you're going to encounter problems like negative probabilities, etc. Instead, you treat this equation as a field equation. Okay, you have a field. Okay, in space and time here as well. It's a vector field because photon has polarizations. This is a scalar field because we don't have spin here. We're going to talk about these details later. But the point is that these are field equations, and you can interpret this field classically. I mean, it's a classical field, nothing quantum here, but you're going to make them quantum fields, and this is that's called second quantization. All right. So because we are going to use simple harmonic oscillator as an analogy, because if you remember that example about a swimming pool, we said that if you have a wave in a swimming pool, quantum mechanically, you can interpret that as a particle. Waves are particles, quantum mechanically. Now, in quantum mechanics, we do not create particles, but in quantum field theory, we want to create particles. How? By exciting this field. Okay, you say I have a field, which is basically a quantum field after promoting this to a quantum field. But the point is that you have a field like depth of water here, say it's a field, and creation of a wave in this example would correspond to, for example, dropping a pebble here. So you excite this field, depth of water here, and that excitation acts like an oscillation, a simple harmonic oscillator at that point. So this field gets excited because you're spending energy there. And that excitation, that oscillation resembles a simple harmonic oscillator, and the energy of a simple harmonic oscillator in quantum mechanics, ordinary non-relativistic quantum mechanics, is given by this expression, if you remember, and n is 0, 1, 2, 3, so on and so forth. So as you increase the energy, if you drop the pebble forcefully, it means that you are exciting this simple harmonic oscillator to even higher energies. So n increases. Okay, but we said that well, you can interpret this as creating more particles. When n equals 0, you have vacuum, no particles around. The simple harmonic oscillator is in its equilibrium ground state, basically. And when you go to n1, 2, 3, you can interpret this as creating one particle, two particles, three particles, etc. So you have a field, and the excitation of that field creates particles. This is particles. This is the general picture we have. But in doing this, you write phi as a Fourier transform and write it in terms of creation and annihilation operators. Then you compare this with what you have for simple harmonic oscillator in quantum mechanics. There we write x, the position of the simple harmonic oscillator, in terms of creation and annihilation operators. And we'll also have momentum of simple harmonic oscillator, which is written in this form with some coefficients, etc. So if you are going to use simple harmonic oscillator as an analogy, so then you should have some momentum corresponding to this field, and then promote these to operators, second quantization. So it should go something like this if you are going to use this analogy. But what's pi? In order to get pi, remember that the Hamiltonian for the simple harmonic oscillator was something like this: m omega square angular frequency x squared over 2. And so you have these two operators, x and p, and you have Hamiltonian operators. So you need Hamiltonian, you need the field, and you need the corresponding momentum. So we have this, we have some understanding of the field, okay, it's the solution of the Klein-Gordon equation, but where is pi and where is the Hamiltonian corresponding to this field? So for this reason, you need to use what you have learned in classical mechanics about Lagrangian formalism and Hamiltonian formalism. We need a Hamiltonian to get this full analogy here. This is the reason we are going to, back to classical mechanics and remind ourselves of what we know about Lagrangian and Hamiltonian of a system. Okay, so with this background, now we are ready to write down the Lagrangian. How? Remember, in classical mechanics, we have this action, which is defined as the time integral of the Lagrangian function. Again, I have to remind you about classical mechanics. In Newtonian mechanics, how you find the position and velocity of a particle under influence of a force. Well, you say F equals ma. This is basically a differential equation. And if you have a formula for force, for example, the gravitational force between a planet and the sun, this is a differential equation. What you need is basically initial conditions, the initial position of the particle and initial velocity of the particle. Then you solve this differential equation and get the final position and final velocity of the particle. This is one way of doing classical mechanics, okay? Another way is to say that, well, I don't care about these initial values or differential equations, etc. What I care about is that I have a particle starting at point x0 at time t0, and it takes a trajectory and it goes to position x at time t. So I want to write down a Lagrangian, a function, and using that an action s, okay. When I minimize this action, I find the trajectory that the particle actually takes according to laws of motion, Newtonian mechanics. Okay, so this is equivalent to Newtonian mechanics. So you have an action, integral of L Lagrangian, x, generalized coordinates and generalized velocities, x dot, and then you say that the variation of this action should vanish, and you get the extremum of this functional, basically, and you get the equations of motion, right? Equations of motion are, in this simple case, given by this equation. Okay, here we are going to use the same method, basically. But remember, if you have a couple of particles, then you're going to have, for example, Lagrangian for a simple single particle is it's kinetic energy, right? And if you have a potential energy, you would write it this way. But if you have n particles, you should add, let me write this properly. If you have n particles, Lagrangian would be the sum of all these. Well, this potential energy can be kind of tricky because potential energy might, for example, uh, depend on the separation of particles. So let me, because we don't want to go details, I'm going to write it just Vk, or for a free particle, we don't have even this potential. So in the future lecture, we're going to talk about details about the potential and other things from classical mechanics. But for now, the point is that when you have more particles, more than one, you have to add Lagrangians of all these single particles to get the total Lagrangian, if you like. Okay, this is a simple point. Now, when you go to a continuum, this has become an integral, basically, right? So this is the reason that S here, let me change my color and get rid of all these. This is to say that Lagrangian, after integration, gives you the action. Now what you need is Lagrangian density, which is a function of phi, phi dot, and gradient of phi, dt y, because this Lagrangian is sum of all these Lagrangians for simple harmonic oscillators that you put at every point in the space. Okay, we are talking about a field, so that field is defined at every single point in the space. So in order to add the Lagrangians of all these, simple harmonic oscillators at every single point in the space, you have to sum over all these Lagrangians. Okay, so this is the reason that L becomes you can write it this way. The sum over all these Lagrangian densities. This is the Lagrangian for corresponding to a single point in some sense, okay? So this summation in classical mechanics becomes, the total Lagrangian becomes this integral, okay? So Hamiltonian as well, we're gonna write Hamiltonian in terms of something like this. Hamiltonian density, Lagrangian density, Hamiltonian density, because we are summing over all these Lagrangians and Hamiltonians defined as single points in space, because phi is a function of space and time, and it's defined at single points in space-time. Okay, so let's start from here. So action would be L dt as usual, but L, the total Lagrangian of the field, is the integral of Lagrangians at every single point, some of them dt, so you can write this as L d4x in a relativistic notation. This is the reason that we use Lagrangian density. In the previous lecture, we didn't talk about these details. We said that we have a Lagrangian for the Klein-Gordon equation. The Euler-Lagrange equation gives us the Klein-Gordon equation. That's it, okay? But now we are adding more details. We have to use, what we used actually in the previous lecture was the Lagrangian density, not the Lagrangian. The difference is just one integration. And as in classical mechanics, we say that, well, we are looking for a path, a trajectory, which minimizes this action. So this can be done using the a variational method. You say that variation S should vanish. I'm not going in details of this. I'm assuming that you are familiar with this from classical mechanics, or probably we should have another discussion about this in a separate session. Okay, so what follows from here is this equation. You can now, because we are working in space-time, special relativity and quantum mechanics, it's going to give you a d over dt dl over d phi dot plus divergence of dl over d phi dl over d phi. Okay, and you can write this. So previously we talked about, in the previous lecture, I wrote this equation, but for the Lagrangian. Now, adding more details, this is Lagrangian density, and another technical point, which is about notation. You can write this in a more, compact form using the Einstein summation notation, and in a compact relativistic notation, basically. So you should be familiar with this. This is dl d phi. Okay, this is what you. So this, when you have repeated indices like mu here, it means that you have to sum over mu 0, time component, 1, 2, 3 for space components. Okay, so this is equivalent to the above equation. Okay, so this is the Euler-Lagrange equation. So what's the goal here? The goal is to find the right Lagrangian density in such a way that this equation, Euler-Lagrange equation, becomes the Klein-Gordon equation. If we can do this, we can find the Hamiltonian and the conjugate momentum, so we can use the similarity between simple harmonic oscillator, where position and momentum, conjugate momentum, are promoted to operators. And then we're going to promote phi, this phi over here, and its momentum, found this way using Lagrangian formalism and Hamiltonian formalism. So we can use the similarity with simple harmonic oscillator. Okay. Now, if you remember the definition of Hamiltonian, what's the Hamiltonian in classical mechanics? Hamiltonian is p x dot minus L. P is the momentum, which is dl over dx dot. Usually it's more common to write q for x because x position is basically generalized coordinate, a generalized coordinate in classical mechanics. It can be an angle, for example, in general. But I'm trying to keep it simple. It's kind of a position, a coordinate. So momentum, the conjugate momentum, is defined this way. It's the derivative of Lagrangian with respect to x dot, the velocity, basically. And for a system of particles, n particles, you have to use this definition, pk xk minus L. So you are summing all over these, particles. So what we get here is something like this. P is dl over d phi dot. In our case, instead of x, we have the field phi, which is a function of x, remember, position. And this is d phi dot of Lagrangian, we said, is the integral of Lagrangian density. We discussed this. So this is basically d phi dot x. I should put x here. This is kind of a summation, right? Summation over all positions of Lagrangian at points y and and phi. Doesn't matter. The order doesn't matter actually. Phi, and also gradient of phi, the spatial derivatives of phi y. Phi. Okay. So you're basically summing over all these Lagrangians, Lagrangian densities at each point y in space. So it's basically an integration. So this means that you can define pi x. In my notations, yes, I've used pi. So you see that for the momentum in this formalism, field theory, you get a momentum density. This is momentum density because we are working with Hamiltonian density and Lagrangian density, okay? It's a continuum limit of a summation, basically. So, and Hamiltonian itself, which is, again, defined by, px phi dot x minus L, right? From classical mechanics, we are summing over all these particles, basically. So you can write this now in continuum limit. It's going to be, so summation goes to integration, and it's going to be pi x phi dot x minus L, right? And you can define this as Hamiltonian density, the spatial spatial integral of Hamiltonian density. So it's the Hamiltonian density. You see, it's the Legendre transform of Lagrangian density. So in classical field theory, here we don't talk about quantum aspects of the problem yet. We are talking about classical field theory. But we are talking about the field defined at each point in space and time. So it means that you are working with these densities, okay? Lagrangian density, Hamiltonian density, momentum density, etc. So for example, the Lagrangian for the Klein-Gordon case would be, Klein-Gordon equation would be this, in this form, and I guess I wrote down this expression last time. Now you can use the relativistic notation to write this in this form, which is more common. Okay. Actually, I tried to follow my notation the previous lecture. So this is Lagrangian. I wrote previously. Now we are writing this, and this means that basically this is d mu phi. When you have two of them, basically, it means that you're summing over this index, and this index goes from 0, 1, 2, up to 4. Space components, and 0 is time component in relativity. Okay, so it's the Lagrangian for the Klein-Gordon equation. If we write down the Euler-Lagrange equations now, here we got that this equation, or in this form. We did this in the previous lecture, but you can repeat it and you get the Klein-Gordon equation. And one very simple note here. So this equation gives you the Klein-Gordon equation, and I'm writing it one more time here. But in a relativistic notation, you can write this in a more compact notation, of course. You can write it this way. Again, in natural units, the speed of light and Planck's constant are unity. Okay, this is the Klein-Gordon equation, and it's more kind of grown-up way. No one writes C and H bar or time derivatives and quantum field theory. So it's very common to use this relativistic notation and also working natural units. So the Hamiltonian is the integral of the Hamiltonian density, and it's going to be what? Pi square now, and pi, remember, dl d phi dot is phi dot, so it can be written in this way, m square, I guess that's a phi square. And again, we had this expression previously, but remember, now we call this Hamiltonian density. Technically, it's Hamiltonian density. Hamiltonian is the volume integral of this. Remember, again, because we are adding simple harmonic oscillators at each point in space, You're adding the Lagrangians and Hamiltonians of these to get the total Hamiltonian for the field, which is this one. So this is Hamiltonian density. Right. Now, one important point here. We work, there was a question actually last time. First of all, yeah, this is a good question actually. Because we are working in a relativistic, theory now, it's kind of odd that we define momentum in this way, because someone asked that, well, in relativity, whenever you have time derivative, you should have a space derivative as well, but you are defining pi momentum in this way, and you are doing Legendre transform in this way, pi dot minus L. So, integrals of these. So why you are getting you prefer time over space? The answer to this question, good question, is that we don't do this. We don't, pick up a preferred time. We have also derivative with respect to space. And instead of Hamiltonian, basically we have a energy momentum or momentum energy tensor, and H Hamiltonian is basically the 0, 0 component of that tensor. Okay, so we have time derivatives dl over d phi dot, and also we have another quantity which is the derivative of Lagrangian density, Lagrangian density with respect to gradient space derivatives. Okay, so let's have a little discussion about this. Basically, you define the, if I can follow my own notation, yeah, dl over d mu phi minus delta mu L. So this is the definition of momentum energy or stress energy tensor, and H, Y, I'm going to give you an answer. Then H Hamiltonian is basically the integral of the 0, 0 component of this tensor, and it can be written in terms of Hamiltonian density, and also momentum of the field would be defined in terms of 0th component of this tensor, and it gives you let's write this as pi x. Okay, if you write this component of the stress energy or momentum energy tensor, you're going to get this expression here. So you see that this pi, which was the derivative of Lagrangian with respect to phi dot, is not the momentum of the field. Okay, it's a conjugate momentum, but the physical interpretation that we have for the momentum of the field is this quantity. Okay, this is the physical momentum which is basically carried by the field. Okay, so you get these two from this definition. Now, you might ask, well, is this a definition or what? Well, not really. You can get this by saying that the action from classical mechanics should be invariant under some space-time translation. So this comes from Noether theorem. In the next lecture, we're going to talk about this, and we're going to derive this expression or derive this definition from their Noether theorem. But for now, again, either you are familiar with this or just trust me for now and take it as a definition for the stress energy or momentum energy tensor. And then we're going to get back and discuss how it basically appears. Okay, so We are in a relativistic setting, and we don't prefer time over space or anything like that. We have a tensor, momentum energy tensor, you can call it, or stress energy tensor. And from there, you get Hamiltonian, the energy component, and also momentum corresponding to the field. This is the Hamiltonian of the field. This is the momentum, ith component of the momentum for the field. Again, in the future, we're going to refine this even more, but for now, I guess that's enough. Okay, so let's move on. We said that for the Klein-Gordon equation, we wrote down a Fourier transform. I should add another, small detail over there too. If you remember, we had this equation again. I write it in a non-relativistic notation to be extra clear. We had this differential equation, and I wrote the solution in terms of a Fourier transform. Following my notations, I guess I used this notation. Let's call it phi pt, or let's do it this way. P a p, which is a function of time, ai px. Okay. And here you can say that, well, because here we are interested in real fields, so phi is not a complex field. We're going to talk about complex fields in the future. But to make it a real field, you can say that, well, a complex conjugate of this coefficient Fourier transform of phi should follow basically this relation, right? Because momentum, or p, the dummy variable, integration variable here, can change from minus p to p without changing the integral, which means that you are working with a real field. Or you can add this conjugate complex term here by writing another term like this. Okay. So in this case, if you look at the complex conjugate of this field phi, you'll see that this term becomes this one, and this term becomes this one. So you are just replacing, swapping these two terms. So phi star, the complex conjugate of phi, is equal to phi, because you've just changed the place of these two terms. It means that you are working with a real field. Okay. So if you do this, or you can stick with this simple relation and write it in this way, doesn't matter, assuming that you have this relationship and you are working with a real field. In any case, when you do this, what we get for the Fourier transform, a double dot p was minus p square m square a. And this was the equation for the simple harmonic oscillator. And from here you see that if you define omega square p this way, p square over m square, what you get for omega p is p square m square. Okay. And energy is positive, basically. Simple harmonic oscillator given by this angular, energy or angular frequency. Okay, and from simple harmonic oscillators, discussion that we had before, for simple harmonic oscillator, we had a Hamiltonian like this. So you can write this Hamiltonian for this simple harmonic oscillator, and from there you can use similar expressions to use to promote this phi to a quantum field. Okay, so we use that trick, similarity with simple harmonic oscillator. But the point is that for that simple harmonic oscillator, this angular frequency or energy, basically, if you put c square here, c4, c square here, dimensional analysis would give you the speed of light back, and then this would become energy of the simple harmonic oscillator. And this is basically the energy of a particle. So you see the similarity between the relativistic relation for energy and simple harmonic oscillator. Okay, in any case, what we have here, just to remind you what we did previously, you write phi x, okay, at a given time, say t at t0, whatever, we work at a given time, a constant time, fixed time, and define phi, the field, or write down a Fourier transform phi for phi at that time, fixed time, as by analogy, using the analogy with simple harmonic oscillator, this way. Omega p, AP, again, my notation would be APA dagger P minus IPX. Okay. So in simple harmonic oscillator, you have X as an operator is 1 over 2 omega A plus A dagger in terms of these operators. Here we promote phi to an operator. We found the Hamiltonian, the Lagrangian, and the conjugate momentum. Now we are ready to use the similarity with simple harmonic oscillator and define the conjugate momentum of the field and Hamiltonian of the field. So I'm promoted to, write down the commutation relations and promote it to a quantum field. Now, this is what we have for simple harmonic oscillator, the position. Now, instead of position, we have phi, the field, instead of changing the position of simple harmonic oscillator, we excite the field. So this is the similarity we have. And also, we had a momentum operator, which was written as minus I omega over 2 angular frequency A minus E dagger, momentum of simple harmonic oscillator. This is the simple harmonic oscillator in non-relativistic quantum mechanics. Similar to this P, because now we know what is the conjugate momentum for this field, we can write down pi x as an operator in this form. Integral of d3p and some minus I omega p over 2 AP minus E IPX minus APE minus IPX. Okay, so you see the similarity here. These are operators now. We have promoted the field and its conjugate momentum to fields. Okay, so these are two operators. Sorry, we have promoted these two fields, phi itself and its conjugate momentum, which are both fields, to operators. So they are quantum fields now. And with similarity with simple harmonic oscillator, you can see that even the appearance of omega here, angular frequency, is exactly similar to what we have in simple harmonic oscillator. Look at this coefficient here, this one. So we have similar expression here and similar expression here, okay? An exact analogy with simple harmonic oscillator. So one more time, why we needed the Hamiltonian for the field? Because we need this. In full analogy, we need x and P from simple harmonic oscillator. So what's this P? Momentum. It becomes pi conjugate momentum for the field when you find the Hamiltonian. So you need Hamiltonian and Lagrangian formalisms. Okay. Now, for a simple harmonic oscillator, you have some commutation relations again. So we have x, for example, I, p, j in 3 dimensions. You have three components for position and momentum. So you can write it as I delta ij, and also xi with xj, different components of the position operator and different components of the momentum operator. These are now operators, remember. Non-relativistic quantum mechanics of simple harmonic oscillator. These are 0. So similar to these, now we write down phi x, pi y as operators should be x, y. Now remember, x and y are the points in space, so we need Dirac delta function instead of the Kronecker delta, and phi x, phi y, pi x, pi y vanish, similar to what we have already. So this is the full similarity between simple harmonic oscillator, and the Klein-Gordon field. Okay, so we have promoted now phi and pi to operators, second quantization, basically. All right, so now you can one calculation. Let's previously we had this calculation, and I promised you to do it in another session. The relation between second quantization of the Klein-Gordon equation and creating a particle with Schrödinger's equation. Another calculation which I encourage you to do is this one. Get phi x, pi x prime. You should get I delta x minus x prime, or in terms of y. Okay, if you use the relationships for AP, if you know A and the relations between these operators, creation and annihilation operators, given in this way, again similar to simple harmonic oscillator, we define it as 2 pi 3. This coefficient of 2 pi cubed is kind of convention. In fact, you're going to have these coefficients here as well, but I don't write them because we're going to refine this in the future again, so I don't pay attention to these coefficients yet, but this is the standard relation that you have. So if you use this relation, you should get this one. They are kind of equivalent. Show this. I encourage you. Show that this is very simple, one-line calculation, but it's your first or second calculation quantum field theory. It is good to do it. And also another calculation too, I encourage you to do yourself, is the Hamiltonian. You can write the Hamiltonian as the integral of the Hamiltonian density, and this can be written as now integral of dp prime, okay, times what? Some expression here. Let's again. This is too simple to here. So show for the next time. Show that you get what? You get this. Let's write it this way. 2 pi 3. Again, I don't write these 2 pi's. I don't care about them for now, but you can write them. A dagger P AP plus AP AP. Okay. Try to get this. This is another exercise if you like. I'll do these calculations in a separate section. I talked about this, but please do them yourself, we're going to get a question here. What is this? Apparently an infinite term, but we'll talk about that. So, and the third calculation I encourage you to do, because if you know what we did here, it's just calculus. It's just simple calculation to show also that H, the Hamiltonian, not Hamiltonian density, and a dagger, the creation operator, is omega p a dagger p, and also H and AP annihilation operator. Remember, all these are operators. Omega p AP. Okay. And this is the third calculation I encourage you to do. Now, and we'll talk about these another session next week, I guess. So now that we've defined momentum operator, momentum of the field carried by the field, this way we defined it in terms of this conjugate momentum pi x del phi x. If you remember already, we had a discussion about this. You'll see this is the volume integral of this. So you can also show that this is, again, with this coefficient of 2 pi cubed p. So if you remember from simple harmonic oscillator, this is the number operator, okay? And also energy, Hamiltonian, becomes what? Hamiltonian, I guess we got Hamiltonian, did I write? Yes, Hamiltonian is here. Hamiltonian is over here. This is the part we need. Hamiltonian, the energy of the field, if you like. This is the Hamiltonian operator, but you know, it's the energy of the field. The energy of the field looks like what? Simple harmonic oscillator in terms of creation and annihilation operators. Now look, what about the momentum of the field? Momentum of the field is very similar. You have this number operated, number of basically particles. If you remember simple harmonic oscillator, it was a number which would go from 0, 1, 2, 3, 4, and we interpreted that as number of particles created. So it's number operator. So if you look at this part in Hamiltonian and compare it to this, you see that you are talking about particles. You're creating particles. This is number of particles, and this is momentum of a single particle. So, and here as well, this is number of particles you have, and this is the energy of a single particle. Remember, omega p is p square m square. This is the energy of a single particle, the energy, relativistic energy expression. So from here you see that you are talking about particles, basically. Excitations of the field can be interpreted as particles. So one more technical detail here. If you remember, we talked about, I'm trying to find my notation previously. I guess I used something like this. A dagger P operating on the vacuum state, 0, would give you something like this in my notation, apparently. Now, if you act one more time with another creation operator with momentum q, you can write the result as some particle, like you have p here, then you create another q. Okay, we're going to talk about this, notation about these quantum states. But the point is that you can show that energy of this is basically omega p, okay, or EP, right, which is p squared, m squared. Try to think about these and get a deep understanding of what's going on. And here, the energy would be omega p plus omega q, okay, and if in general, you should write p 3 dimensions a vector, so you should write So you are summing over energies, okay? And if you add more particles, basically you can say that AP, A dagger Q, etc. on 0 has energy, this state has energy of omega P plus omega Q plus, this is the total energy in that quantum state, okay? So, remember, one important thing is that what I mentioned here, where was that? Now I should find it, which is hard. Here. I said pick a fixed time and work there. Just write this Fourier transform, for example, at a fixed time. So here I don't have any time dependent. Previously we talked about, we wrote down Fourier transform like we had a term like this next to this, if you remember. Now I'm going to talk about that. Here I don't have time. Okay. Here we are working in at a fixed time. Okay. Now let's this can be called the Schrödinger's picture, because remember what we are doing here is promoting phi, the quantum field, to an operator. In the Schrödinger's picture, operators are time independent in quantum mechanics. In Heisenberg's picture, they are time dependent. So basically, this assumption here meant that we were working in the Schrödinger's picture. So at a fixed time, there is no time dependence in this expression here. You can move to the Heisenberg picture by defining, in my notation, it was like phi x and t. Now, this is the Heisenberg picture. How you define a time-dependent operator in quantum mechanics? Using the Hamiltonian, you write it I, H, T, phi x. This is the operator in Schrödinger's picture, time-independent. This is the operator in Heisenberg's picture. Simple, ordinary quantum mechanics. You define the Heisenberg groups, time-dependent operators like this, and we have also from, again, ordinary quantum mechanics, the Heisenberg's equation of motion. For any operator, it would be, there is a constant h here, but I'm not writing it because I'm working natural units, remember. So it would be, okay, so this is the Heisenberg's equation of motion, and this is the way we make our Schrödinger's time-independent operators time-dependent. Now you're going to do this, and if you do this, what you get, phi x and t would be, I don't have them here, I don't think so. Okay, we had this. Okay, let me be very careful here. We started with this expression phi x, time independent, Schrödinger's picture, and we wrote something like this: APEIPX, okay, plus a dagger, another term, E minus PX, and this is similar to position operator in simple harmonic oscillator. And remember, this is basically the complex conjugate of the first term to make phi real. Okay, so this was the reason that we had this form for the Fourier transform. Now, if you write phi xt in the Heisenberg picture, which is basically, there's no need to write this h, because when you write phi x and t, it means that your operator also depends on time, and you use this relationship, you're gonna get a p e minus I omega pt, or because we called it energy, let's call it EP T plus IPX plus a dagger P E plus IEPT minus IPX, okay, with some coefficients here, okay. Basically, it's 1 over square root of 2 omega p or EP, right? And pi defined in a similar way, but basically it's the phi xt over dt. It's phi dot, right? So we don't need to write the explicit form of pi here. The point is that when you work with time-dependent field and its conjugate momentum, you have this expression in which the energy term, this is the energy term, omega p or EP, comes with a minus sign next to the annihilation operator, and next to the creation operator, it has a positive sign. Unfortunately, this is not usually mentioned, but this is very important. This minus sign, technically, mathematically, comes from this definition. When you try to make your, time-independent operator time-dependent using Heisenberg picture, you get this minus sign here. Let me try to show it clearly here. This is negative and this is positive. And also there is another more physical reason for that. It's because when you go to lower energies, we want to recover Schrodinger's equation. Okay, in the Schrodinger's equation, what's the Schrodinger's equation for a single particle, free particle? It's I h d psi dt minus psi over 2m h squared, something like this, right? This equation, the free solutions for this equation have this form minus what's going on? My iPad is acting crazy. E t plus I px, okay, right? So you need this minus sign here in order to get positive energies in non-relativistic quantum mechanics. And we want a Klein-Gordon solution which reduces to this form in non-relativistic case, all right? So, and in fact, another exercise, I don't know, fourth calculation for you to do is that if you use this ansatz, phi xt psi xt e minus I guess my iPad is kind of tired, so maybe it's time to finish this lecture. T, okay. So if you separate the rest energy of the particle using this term, okay, then in the Klein-Gordon equation, I wrote down C and H here on purpose, just to show you the full expression, but here I don't write them because it's natural units. You have to recover H bar and C. But the point is that when you try to get the non-relativistic regime from Klein-Gordon equation, the non-relativistic regime corresponding to this relativistic equation, you can use this ansatz. Okay, if you plug in this expression here and assume that the particles have very small kinetic energies with respect to their rest energy, you're going to recover the Schrödinger's equation for psi. Okay, so here as well you see that we have this minus sign in front of this. This is another calculation that I encourage you to do, and I'll do it in question and answer session or whatever we call it. And it's important to do it, simple but still important. So the point is that the energy or frequency term in this exponential for the Schrödinger's case comes with a minus sign. So this is the reason we put a minus sign here in the Klein-Gordon Fourier transform. And the other term is just the complex conjugate of that, so you get another, a reverse sign. Long story short, when you write down the field, the Fourier transform for the Klein-Gordon field, remember to put a minus sign for the energy next to the creation operator, annihilation operator, sorry, here. Okay. And a positive sign next to the creation operator. This is the convention, and it comes from this basically Heisenberg picture, and also it's related to Schrödinger's equation at low energies. Okay, so so we have a couple of calculations to do for the next time, for the next session, not next lecture. It's going to be a separate session, and I guess that's it. I've done whatever I plan to do. Well, next Monday we're gonna have this session on these calculations and a couple of questions which were asked in the Zoom meeting last time, and I'll look at your questions for this meeting. But in the next lecture, basically, we are going to um, have a quick look at the second quantization of the Klein-Gordon field, and after doing some calculations and getting fluent with these, we're going to move to the radiation field and try to quantize the electromagnetic case, which is the radiation field, the vector potential.